Welcome back. The topic for this video is pH and pOH. So remember that we are talking about acids and bases, and the concentration of the hydronium ion and the hydroxide ion concentration, they are critical in determining a solution's properties and chemical behaviors. And so it's important that we're able to measure the hydronium and the hydroxide ion concentrations, and it helps to have them in numbers where we're not constantly having to use scientific notation. And so this is where pH comes in, right? When we are trying to express quantities that can span many orders of magnitude, right? Because remember that kW value runs down to 1 times 10 to the negative 14th. So your hydronium concentrations can basically span anywhere from 1 down to 1 times 10 to the negative 14th. So we're going to use the logarithmic scale to deal with this. And whenever you see a lowercase p symbol in front of something, that lowercase p tells you that you are taking the negative log of that value, right? So x in this case doesn't mean anything. It's just a placeholder to tell you that if we have a p to anything, that is equal to the negative log of that entity, right? And then the anti-log, so on the right-hand side we have our anti-logs. Whatever that species is equal to 10 to the negative p of that species. Okay, so for example, if we're looking at that hydronium ion concentration, remember that oftentimes we will look at that hydronium ion as being interchangeable with the hydrogen ion, which is the H+. Right, so H+ we consider to be approximately the same as that hydronium ion. And so that's why instead of saying pH3O, we just say pH. And so pH is equal to the negative log of the hydronium ion concentration. And then vice versa, if we have the hydronium ion concentration, that is equal to, if we have the pH, if we have the pH, then 10 to the negative pH gives you that hydronium ion concentration. So it just depends on what you're given. If you are given the hydronium ion, then you can find pH using the negative log. If you are given the pH, then 10 to the negative pH will give you the hydronium ion concentration. And we can interchange that with the hydroxide ion. So pOH is equal to the negative log of the hydroxide ion, and then the concentration of the hydroxide ion is equal to 10 to the negative pOH. Okay, and then we have these terms based on whether we have the same hydronium and hydroxide ion concentration or if we have more or less of one. So at neutral, we're going to have equal amounts of both, right? The concentration of the hydronium ion will equal the concentration of the hydroxide ion, and we'll have a pH equals 7. Okay, so just keep in mind that as long as you're at 25 degrees Celsius, then that means that the hydronium ion and the hydroxide ion concentrations will be 1 times 10 to the negative 7th molarity. And so that's where you're getting that pH of 7. If you are acidic, then you have a higher concentration of the hydronium ion, and if you do that, you should have a pH that is less than 7. And then basic, you're going to have a hydronium ion concentration that's less than the hydroxide ion concentration, and so that's going to give you a pH that is greater than 7. So the relationship we've already seen between the hydronium and a hydroxide ion concentration in terms of Kw, right? Kw equals the hydronium times the hydroxide ion concentration. We can manipulate this to use our P values, our pH and our pOH. And so if we take the negative log of both sides, right, the negative log of Kw and the negative log of hydroxide and hydronium ions multiplied together, we can then separate out. Remember, if you have a log of values A times B, you can separate that out to say the log of A plus the log of B. Okay, so that's what they're doing here. If you've got the two concentrations multiplied together within the log, you can separate them out by adding the two together. And then we know that the negative log of the hydronium ion concentration, that is equal to your pH. And the negative log of the hydroxide ion concentration, that's equal to your pOH. And so, again, taking the negative log of Kw, you get pKw equals pH plus pOH. And because we know that Kw is that value of 1 times 10 to the negative 14th, if you take the negative log of 1 times 10 to the negative 14th, you'll find that you get back a value of 14. And so 14 equals pH plus pOH as long as you are at 25 degrees Celsius. Of course, this would change at any other temperature. So just a quick summary and overview table of hydroxide and hydronium ion concentrations and what value of pH or pOH that you would be given. List of common household products that you will find, whether they are acidic or basic. So of course we know any of our fruit juices like lemon, lime juice, those are going to be acidic. Vinegar is a popular acidic home product, right? Many of us have done that vinegar baking soda reaction before, and it can be very useful for when you're cleaning. Stomach acid, coffee, all of these things are considered acidic. And then most of your bases are going to be your household cleaning products like bleach or ammonia. Milk of magnesia is another popular one. And we can measure the pH in several different ways, right? We've got a pH meter that will tend to give you the most precision, but sometimes if you don't properly calibrate that pH meter, you could get values that they might be very precise but very inaccurate. So it is helpful to have your litmus paper or some type of a pH indicator so that you can just double check that that pH meter is giving you both an accurate and a precise value. So the next section is a review of General Chemistry 1. So in Gen Chem 1, hopefully your instructor had you memorize your 6 strong acids, right? So you've got your 3 halogens. The one that's not included is fluorine. So fluorine is considered hydrofluoric acid as a weak acid. But the other 3, hydrochloric, hydrobromic, and hydroiodic, those are all strong acids, as well as nitric acid, sulfuric acid, and perchloric acid. So one of the phrases that you'll find on the internet that can help you memorize this is, "So I brought no clean clothes." Okay, so in bold you can see the SO represents your sulfate ion, and then the I and Br represent your halogens. NO represents your nitrate ion, and then Cl, your halogen chlorine, and then ClO is the perchloric acid. Now, depending on your resources, sometimes you'll also see an HClO3, but I won't test you on that one. So you've also seen this in General Chemistry 1, where your strong acids are going to fully dissociate into their ions. And so if that acid is reacting with water, of course it's going to donate that hydrogen to water to give you that hydronium ion, as well as the remaining species. But what we care about is that hydronium ion, right? So all of your hydrochloric acid, let's say you had 3 moles of your hydrochloric acid, that is going to fully dissociate to give you 3 moles of your hydronium ion. Okay, so when we say that we have a 3 molar hydrochloric acid, we are essentially saying that we have a concentration of 3 molar of your hydronium ion. Okay, so those are interchangeable as long as we're dealing with a strong acid. And then same thing for the bases. We have 8 strong bases, and most of those are going to come from your alkali metals and your alkaline. So your first 5 strong bases are going to be the center 5 alkali metals in group 1 attached to your hydroxide ion. And then halfway down that list, you've got your potassium, and if you'll go across, it will be calcium, strontium, and barium of your alkaline earth metals. Okay, so those are your 8 strong bases. Those can be memorized probably based on the periodic table. Group 1 and Group 2 metal hydroxides. So just like your strong acids, your strong bases are going to fully dissociate in water. This time I put the water over the arrow just because it would be redundant to have it on both sides. But when that base dissociates in water, it forms your hydroxide ion concentration. And again, if we have 3 moles of sodium hydroxide, that is going to fully dissociate into 3 moles of your hydroxide ion concentration. So if we say that we have a 3 molar concentration of sodium hydroxide, again, we are saying that the concentration of hydroxide ions is 3 molar as well. And cannot emphasize this enough, this only happens with strong acids and strong bases, which is why you have to have this list memorized. So that you know whether you're dealing with full dissociation or if we're dealing with equilibrium constants, which we'll see in the future in this chapter. So we're going to do a little bit of practice with pH and pOH. The first set of examples, they're asking us to calculate pH and pOH of each of the following. And of course, it's at 25 degrees Celsius. And all that does is tell us that the Kw value is equal to 1 times 10 to the negative 14th. And for the purposes of this class, we're going to assume that the Kw and the pKw, remember pKw was equal to 14. We're just going to assume those to have infinite sig figs because they won't really limit us. That is technically 1.00 times 10 to the negative 14th, and so that is 14.000 for our pKw. Okay, so no issues with sig figs from those values. So in this first example, they're giving us 0.2 molar of hydrochloric acid. So remember, when they give you that 0.2 molar of hydrochloric, they are telling you that you have the same amount, 0.200 molar concentration of your hydronium ion. And we know that because hydrochloric is a strong acid. Okay, so because it's a strong acid, we now know the concentration of the hydronium ion. And so if we're looking for the pH, right, pH is going to be equal to the negative log of that hydronium ion concentration, the 0.200. Okay, and we're going to ignore units because pH does not have a unit. So when we're looking at sig figs for logs, I know we have looked at logs before, but I want to write this down again and write it down, and then I might have to erase it for space. But the number of sig figs in our ion concentration values that is going to be equal to the number of digits after the decimal in our pH and pOH values. Okay, so you can review sig figs and logs, but basically the number of significant figures within the log. So here we've got, say, 3 significant figures. that tells us the number of decimal places or the number of digits after the decimal that we need to report our pH and our pOH values. So if we have 3 sig figs in our number, then when we put this into the calculator, we get that pH will be equal to 0.699, and that is 3 places after the decimal. Okay, and then they also ask us to calculate the pOH. So once we have the pH, remember that pKw is equal to 14, and so we can simply take the pKw value minus the pOH, right? Because we have this equation, pH plus pOH is equal to 14. So 14 minus the pOH, 14 minus the pH of 0.699 will give us back the pOH. And subtracting out, we're going to assume 14 to have infinite sig figs, and so we want to report out 3 decimal places, and that gives us 13.301 for our pOH. Okay, and then in the second example, again, remember that sodium hydroxide is one of our strong bases. And so they are telling us that we've got 0.0143 molar of the hydroxide ion. Okay, so when we take the negative log, because we're talking about the hydroxide ion, that's going to give us the pOH. So for B, the pOH is going to be equal to the negative log of 0.0143. Okay, again, this has 3 significant figures. The zeros before the non-zero digits don't count. And when we put this into the calculator, you get back 1.845. Now notice this is 4 significant figures, but that's not what the rule says. The number of significant figures in ion concentration is equal to the number of digits after the decimal. So if we have 3 significant figures within the logarithm, we're going to have 3 decimal places after the decimal. Right? And so our pOH is 1.845. And to find the pH, of course, you're just going to do 14 minus. So pH will be equal to 14 minus the 1.845. And assuming infinite sig figs for that 14, you're going to report this out 3 decimal places and get 12.155. Again, because addition and subtraction, remember that's based on the number of decimal places again, so 3 decimal places out for both. Okay, and we've got one more example. In this example, we're using the anti-logs. They're asking what are the hydronium and the hydroxide ion concentrations if we're given a pH of 6.52. So remember that if we're trying to find the hydronium ion concentration, that is going to be equal to 10 to the negative pH. So plugging this in, hydronium ion concentration will be equal to 10 to the negative 6.52. Now we're doing the opposite here, right? We're doing the anti-log. So the number of digits after the decimal in pH and pOH values, that's only 2 decimal places. And so that tells us that our hydronium ion concentration needs to be 2 significant figures. And so of course we want to plug this into the calculator to get a number back. We don't want to leave it as 10 to the negative 6.52. And so that comes out to be 3.0. Again, 2 decimal places gives me 2 significant figures for the hydronium ion concentration, and then times 10 to the negative 7th molarity. And don't forget to add those units back in. Okay, now they also want us to find the hydroxide ion concentration. So, of course, you could take that hydronium ion concentration as well as your Kw value, that 1 times 10 to the negative 14th, and solve it that way. But personally, I like to first find the pOH and then take the 10 to the negative power. I just think that that tends to be easier math. So what I would do is I would take the pOH is equal to 14 minus the pH value that they gave me, the 6.52. Okay, and so the difference between those, I would get the pOH equals 7.48, and then the hydroxide ion concentration equals 10 to the negative 7.48. Okay, again, 2 decimal places here in the pOH value, and so I need 2 significant figures in my answer. And that will give me 3.3 times 10 to the negative 8th. And that would be, don't forget our units, that would be in concentration of molarity, and those 2 decimal places right gave me 2 significant figures in my hydroxide ion concentration. And then just to wrap this up, if we're trying to determine whether this is acidic, basic, or neutral, remember that as you get more negative in your magnitude, that means your number is decreasing, right? So this 10 to the negative 8th versus 10 to the negative 7th, that means that the hydroxide, or we'll start with the hydronium ion concentration is going to be greater than your hydroxide ion concentration. And again, that's because the hydronium ion is about 10 to the negative 7th versus the hydroxide concentration is about 10 to the negative 8th. And so if we have a higher concentration of hydronium ions, that is going to be an acidic solution. Okay, and again, we know that because when we look at that pH, the pH is less than 7. Okay, so that ends our discussion on pH and pOH.